Hello, my name is Ezequiel Abreu, and today I will be talking about the project I am currently working on called Toward a Tool to Evaluate Visual Behavior in Multi-Device Environments. The project is part of the semester-long project for ECE724 Ubiquitous Computing with Professor Andrew Kuhn. For this project, the Pupil Labs eye tracker was used. The eye tracker is displayed on the model on the left. The headset is a device that has three cameras, two that are meant to record each eye, and the third one that records the world in front of that person. The eye tracker headset was made by a team of people in Berlin, Germany. It has a USB to connect to a computer, and when connected to a computer, it has its own software used to record, play, and export the videos. On the right side of the screen, you can see two sets of pictures. The one on the top is a picture of the pupil capture software. The software is used to record videos. It will display a red dot that is the best estimate of where the user is looking at. For best results, it is best to calibrate it by using the C button. The picture on the bottom is the pupil player. It is used to replay any videos acquired. It is also used to export videos into suitable files and to extract any raw data like pupil position and gaze position. For this project, I mainly focused on gaze position. The purpose of this project is to evaluate the visual behavior of a person, depending on where they are looking at on a large surface. For this project, I used a projector for the large surface. Four targets were placed on the surface in order to know where the user was looking at exactly. The targets were labeled TR for top right, TL for top left, BL for bottom left, and BR for bottom right. The reason for the targets is to know how well of an estimate the eye tracker is making in accordance to where the person is looking at. Mainly two sets of videos were taken, one looking straight at the projector and another looking at the projector from an angle. As you can see, these images are from both videos. The projector had four targets as mentioned. Now the targets were measured with a ruler in inches. It was measured from left to right and from bottom to top. The locations of each target were 15 and 9 inches for BL, 15 and 27 inches for TL, 53 and 9 inches for BR, and 53 and 27 inches for TR. In order to find the projector from the frames of the video, MATLAB was used to find the threshold image of the frame. So what the threshold image does is separate the light and dark image of a frame between black and white. The picture is a binary picture where black is 0 and white is 1. A problem encountered was that there may have been a lot of white in the background which could cause there to be some noise from different objects. To avoid this, I put the projector in front of a dark blue curtain to try and have a difference in color. What happened was that the world video would still see some things in the background that would be represented as white, as shown in the two pictures to the left. What I did to fix this was create a binary image that would be used as a mask to mask out all the unwanted white noises and keep only the projector as white. As you can see, the images in the right only show the area of the projector in white. In order to place the gazes on the image using the pupil player, I exported the raw data of the video. The file gazepositions.csv would be exported and then imported into MATLAB. The CSV file had multiple columns of data, but the ones used for this project were normpos_x and normpos_y. The thing about this was that the gaze locations are between 0 and 1, which is the range of the world view. In order to put them into the image, I had to use an algorithm that would transfer it there. The picture was 1280 times 720 pixels, so to put the gazes in the desired location, I used x as the gaze of 1280 times normpos_x and y as 720 minus 720 times normpos_y. The reason that y is 720 minus 720 times normpos_y is because in the image the lowest y starts at the top instead of the bottom, and the normpos_y represents it as if it were to start from the bottom. These are the gazes transferred into the new frames of each video. From the threshold image you can tell more or less where the targets are because of the gaze positions. The gazes that are nowhere near the targets are when the eye leaves one target to look at another. For this project, it was desired to get the origin, which is the middle of the projector. To find that for the straight image, it was easy because the whiteness was distributed equally. So the origin was just the average X and Y position of every white dot. It was a bit harder for the angled videos because the whiteness was stronger on one side, and so finding the X and Y average would just pull the origin off more to the stronger side. So to fix this, I used an algorithm to find all the corners of the projector. Once the corners were found, another algorithm was written to find the intercept of the two diagonals, which for a rectangle is the middle. The image on the right shows the origin represented as a red cross and the diagonals intercepted at the middle of the projector. In this image is where the gazes are plotted one by one. The blue circle represents the gaze, the red circle is where the target is located. The blue and red lines represent the distance of each to the origin. Again, the red cross represents the origin. In the top left corner, you can see the numbers calculated from this. It includes the distance of the blue dot to the origin, the x and y coordinate of the blue dot in respect to the origin in both pixels and real-world inches. It also includes the quadrant that the blue circle is in respect to the origin. The slope of each dot is included in this too. Probably the most important is the error percentage, which calculates the percentage of the error of how far the estimation of the eye tracker is to the origin. Again, here's the same information, but with the angled video. This time the circles are in the fourth quadrant. As mentioned, the error percentage is very important because it shows how much error there is based on where the user was looking to where the eye tracker thinks the error is looking. In this project, the average of each target's gazes were measured and put into a chart. This first chart is the percentage error when looking straight from the projector. The BL has 39.75% error. BR has 49.74% error. The TL and TR have 20.26% and 10.51% respectively. The two top ones had the least amount of error, as you can tell. The reason for this is that the top ones were more at eye level than the two bottom ones, so the eye tracker had an easier time tracking the gaze for these two. The percentage error for the angled video was a little different. The BL had 44.95% error, the BR had 39.82% error, TL had 19.1% error, and TR had 46.43% error. This tells me that the person's head might have been more aimed towards the top left than any of the others, and that is why it probably gave the least amount of error in the top left and why the others basically had similar percent errors. This is one of the videos exported from the pupil player. As you can see, the green dot is where the person is looking at. As you can see, the person first looks at the top left, then the top right, then the bottom right, then the bottom left. This is the second video from pupil player. As you can see, the person again looks at top left first, then top right, then bottom right, then bottom left, and does the same rotation again to make sure that all locations are looked at. To conclude, the results show how the targets had very different results when it came to error percentage. In the video in front of the projector, the top targets had the most accurate results. This makes sense because these are more eye level than the bottom target. It is like when you try to see something on the ground when your head is facing the wall. You may see the ground, but you feel that you are forcing your eyes to look down. The angled video only had the top left with accurate results. Again, this could be because the user's head may have been facing the top left more than the other three, and the user may have been forcing his eyes to look in another direction without moving his head. In conclusion, the top left target had the best results in both videos. Maybe this may say something about how accurate the recording is when the eyes are looking in that direction. Thank you.